In this lesson, we want to talk about a concept by the name of capacitance, or by the term capacitance. Now, when you think about the word capacitance, right, one of the things that comes to mind is capacity. When you think about capacity, it means, how much, you know, um, something can hold within a, a particular space, right? Now, as it relates um, to module one of the unit one syllabus, we need to talk about the specific term capacitance. Now, capacitance is linked with capacitors, right? Capacitors are devices that are able to store charge, right? And we're going to look at that. We're going to look at how capacitors behave and what capacitance really means to us in physics. All right, so we'll kick start it by first looking at what a capacitor is. So a capacitor is a device for storing charge. All right, it says that a capacitor consists of two conductors with an insulator or an empty space sandwiched between them. It says that the empty space or the insulator is called a dielectric. So you're going to hear us talking about dielectric, and it is simply either air or an insulator. Now, the dielectric of a capacitor helps to, you know, increase the storing capacity of the capacitor. All right. So depending on the different type of insulators that are used, that will determine how much charge will the capacitor itself store. Now it says to charge a capacitor, charge must be moved from one of the conductors to the other. It says here that it takes work to remove electrons from a conductor. It also takes work to place an electron or electrons rather on a conductor that has received electrons. And since if you can imagine you taking electrons and putting it on a conductor that already has electrons, then there's going to be an electrostatic force of repulsion that needs to be overcome. So you can expect that work has to be done to do that. And it says, thus, in charging a capacitor, work has to be done by an external agent. Now, whenever we're talking about charging a capacitor, it's simply taking charge and putting it on the plates of the capacitors. We'll soon talk a little bit more about, how capacitors look and all of that. But here it tells us that in order for us to do this, right, we definitely are going to need some amount of work to be done. And in order for us to do this work, we need an external agent, and we refer to that external agent as a battery, right? And that battery is generally placed between the conductors. Now, as it relates to calculating the work done to charge the capacitor, right, we can use this equation here, right, that says work is equal to the charge multiplied by the potential difference. All right? And that will determine or will tell us the amount of work that was done to charge the capacitor. If you can recall that potential difference V is equal to the work done, right, divided by the charge, then by way of just rearranging this equation, we could have found the work that was done to move those charge from one plate to to another plate. All right. Now it says to us that whenever we are charging a capacitor, right, we will create what we call a potential difference between the plates of the capacitor. Okay. So once there are two charged plates, positive and negative plates being charged, then what we essentially have is a potential difference, which just tells us that you have a potential of positives and a potential of negatives. All right. Now, experiment has shown to us that the amount of charge on a capacitor is directly proportional to the potential difference across the conductors. So it tells us the more charge we place on the capacitor, it's the more potential difference that will be set up across the capacitor. And it also tells us that the more charge we have on the capacitor, we have stored on the capacitor, it's the more work it's going to require for us to charge that capacitor. And in total, we're saying that the potential difference across the capacitors are also going to be directly proportional to that. Whenever we have a directly proportional relationship, so if Q is directly proportional to, let me erase that. If Q is directly proportional to V, then there's always a constant, right? A constant of proportionality. Now, whenever we're talking about capacitors, right, that constant of proportionality is going to be known as our capacitance. So this is what we're saying. We're saying that the charge stored on the capacitor is equal to C times V, where C is a constant value, which is known as the capacitance. Okay? And the capacitance tells us, from an equation standpoint, it tells us that the capacitance C is equal to the charge stored per unit potential difference. So if you're ever asked to define the capacitance, you have to define it from the standpoint to say it's the amount of charge that is stored in a capacitor per unit potential difference. And with that being said, we can see here that the units for capacitance can either be what we call coulombs per volt, or there's a unique name for capacitance. We refer to it as farads. And you can also read the notes here to see what we're saying. All right? So the units for capacitance is farads. You will hear us using that more often. But you can also realize that because charge is in coulombs and volt, our potential difference is in volts, then you can also see why we say that C times, C divided by V, which is the same thing as saying coulombs per volt. All right? Now, just a simple question here that asks us, how much work, right, or rather, my bad, how much charge flows when a 3-volt battery is used to charge a 4 microfarad capacitor, right? So they want us to find the charge that is stored. So first, we need to recall our equations that links capacitors. So we know that Q is equal to C times V, right? I believe we can simply find what the charge is by just going ahead, putting in the information, because We know the potential difference that is applied to the capacitor. We know the amount of charge that can be stored per unit volt, right? So that is the capacitance. So Q is now equal to the capacitance, which is 40 times 10 to the minus 6 times the voltage, which is 3 volts. We can now get a value to say that our charge stored is 12 microcoulomb. All right. So that solves this particular question. All right. Now we move along. Now, similar to when we had a wire that had some type of resistance, right? We said that there are factors that can affect the resistance of a wire, right? Where we recall that if we have a much thicker wire, then that will reduce its resistance. So there are certain relationships that exist whenever we are talking about resistors and wires, and there's also some type of relationship that exists whenever we're talking about capacitors. Now, experiment has also shown to us that the capacitance of a capacitor is directly proportional to the area of the plate. So here we have a capacitor, right? You have different types of capacitors, but for this now, we're dealing with parallel plate capacitors. So with a capacitor, you have two plates. You have a top plate and you have a bottom plate. Quite often, one plate is going to be positively charged, one is going to be negatively charged. So this, let's just imagine this plate is positively charged, this plate is negatively charged. Now, what we're saying here is that based on the area of this plate, right? Based on the area of the plate, top and bottom, that determines the capacitance of the capacitor. Now, let's look at this, guys. If you have a much larger surface area, right? Don't you believe that more charge can be stored on this area versus this diagram right here? This one can store a limited amount up to a certain amount of positive charge, right? But with increasing the area, you increase the capacity of the capacitor, meaning that you can store more coulombs of charge per unit volt. All right? So that's what we're saying here. Now, there's another factor that affects the capacitance, and that is what we refer to as the separation distance between the plates. We generally refer to that as D. So this D that you're seeing right here, that's what we refer to as the separation of plates. Now imagine that you have a sandwich, right? And inside of that sandwich, let's just imagine that we have a bread sandwich here. So this is our lunch to go to school. We have our lettuce inside, right? We have some meat, we have some tomatoes and all of that. And then now you sandwich that with another bread at the bottom. You understand? Right? So we sandwich that with another piece of bread. So this is just a sandwich. Just like that's typically what a capacitor, is in a sense. Now, this is what we're saying. If I were to increase the distance of separation, meaning that if I were to do this is my top plate, right? And I shift the bottom plate further down so that the distance of separation is much greater, right? So this is now the entire capacitor. This is now the entire capacitor. So what we were saying here is that There's a distance between the two plates. And now, if we increase this distance, right, we're essentially reducing the capacitance of the capacitor. So with that being said, at first we said that by increasing the area, we increase the capacitance. But by increasing the distance of separation, we reduce the capacitance. So with all of that being said, we can tie it into an equation to say that the capacitance is equal to epsilon times A, which is the area, divided by R. So here's another equation that we can use whenever we're talking about capacitor. We looked at one equation to say that capacitance is equal to Q divided by V. But now this one is when we are looking at the literal capacitor before us and thinking about the area and the distance of separation. Now mind you that epsilon is what we call the electrical permittivity. And that is a constant. Remember we said whenever you have some proportional relationship taking place, there's always a constant of proportionality. Now for this type of relationship, we have what we call the permittivity, the electrical permittivity. And when we talk about electrical permittivity, it's the ease through which an electric charge can flow through. All right. So now E is what we say we call the electrical permittivity, right? If you guys can recall when we're talking about electric field and so forth, then you would also understand the whole aspect of electrical permittivity, right? But hear me out now. There's a relationship between what we call K, right, which is the dielectric constant, right? So K is equal to the electrical permittivity of the medium, right, divided by the electrical permittivity of free space. Now, each material has an electrical permittivity, right? And if I were to divide that by the electrical permittivity of free space, I now get a constant which we call the dielectric constant. Follow me? So that equation a while ago that says C is equal to epsilon times A divided by D, I can do a quick thing right here to say that epsilon is equal to K times epsilon naught, right? So C is actually equal to K times epsilon naught times A divided by D. And we're going to see that more often, so that you have to just remember that these things do exist, right? You know, in terms of the electrical permittivity and the dielectric constant, okay? Now, before we go there, let's just recall that epsilon naught is this value right here, right? That says that it's equal to 8.85 times 10 to the 12 coulomb square Newton per meter square. So that's the actual value for the electrical permittivity of free space. So epsilon naught, right, is equal to that value. Good, so please remember that. As we talk about capacitors are electrical devices. So you will always see capacitors in circuits, you understand? Because there are times when you will need to store some amount of charge in a particular circuit, right? So there are certain arrangements of capacitors. Capacitors can be in series and it can be in parallel. Good. Now we need to derive a formula for when we have capacitors in series. Now, according to Kirchhoff's voltage law, it states that the sum of the EMF in any closed loop, right, in a circuit is equal to the sum of the potential differences across or in that same loop, right? So this is what we're saying, that my total V, right, is equal to V1 plus V2 continue all the way up there. Now, if we can recall something spectacular that about our capacitance. Capacitance is equal to Q divided by V, right? So if we make V become the subject, we can clearly see that Q, right, is divided by C. That's what V is, if we were to transpose the equation. So by way of substituting V into this Kirchhoff equation, right, I am left with my total voltage, which is the same thing as this. My total charge divided by CT is equal to Q divided by C1 plus Q divided by C2 plus Q divided by C3, and it continues depending on the amount of resistors, depending on the amount of capacitors that you have. Now, you might be wondering, why is it that the Q remains constant? You have to remember that when things are connected in series, right, the current remains constant. So imagine that this is a simple circuit, and we have capacitors connected in series. The current flowing in the circuit is going to be constant in a series circuit. So if the current is constant, that means that the voltage is not the voltage, but the charge is also constant, because current is the rate of flow of charge. So if we want to consider charge is going to equal to current times the time. So whatsoever the current is, that's going to be the same amount of charge flowing in the system. So this is the equation for when we have capacitors in series. Very important equation, right? Because we're going to utilize that when we look at different types of circuit problems. Now, let's consider, this is the same, well, not necessarily. Let me see what's happening here. Maybe I did note that. Okay, yeah. So it says that note that this equation is similar to the equation for the total resistance for a number of resistors in parallel. In terms of how the equation looks a while ago, right? That says 1 upon CT is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3. We're saying that the equation here, right, is similar to when we're trying to find the total resistance of a number of resistors in parallel. Good, and this is what a series circuit looks like when you have capacitors connected in it. Each capacitor is going to have its own voltage, because we know that in series circuit the voltage is divided, right? And we know that there is a total voltage within the system coming from the power source that is connected in it. Now, for capacitors in parallel, we can also come up with an equation, right? Now, let's just look back at this. It says that according to Kirchhoff's current law, we know that the sum of the current entering a node or a junction is equal to the sum of the current leaving that junction. And therefore, we could state that to say that Kirchhoff's first law states that I1 or IT rather is going to equal to the sum of the current going into or leaving the junction. But if we can recall what charge is equal to I times T, right? And whatsoever the total time is in this scenario, right? It's the same time that will be experienced across all the other capacitors, so to speak. So we could just simply replace, could replace I, right, for Q divided by T. We know that T are going to cancel out. So we're left with the capacitance, the total capacitance for capacitors in parallel is like summing the capacitors. So whenever you have capacitors in parallel, you sum the capacitors, right? And we said that note that this equation is similar to the equation for the total resistance, right, of a number of resistors in series. Okay? So in terms of the structure of the formula, it is similar. Good? Let's look at this problem. Not a hard problem. It says that we have three capacitors that are connected as shown in the diagram here to a 12-volt DC supply and are fully charged. It says calculate the net charge CT of the combination. It says calculate the net charge. Yeah, my bad. Let me check A again. A says calculate the net capacitance rather, CT. Then now B says calculate the net charge, right, QT of the capacitor. It also goes on to say that we should calculate the charge Q1 on the 2 microfarad capacitor, and it also wanted to find Q2 on the 4 microfarad capacitor as well. So we must solve that question, right? And we could start off by recalling that capacitance is equal to Q divided by V. Good. So we could start off with that. As a matter of fact, no, we don't need to start off with that, We want to find the net capacitance. So what we need to do, right, is to look at the circuit. So right here we have a circuit, right, where we know that, we have the voltage connected here. Then this this capacitor is connected in parallel with the power source. Then we're seeing two capacitors that are connected in series, but those two capacitors are also connected in parallel with this 6 microfarad capacitor. So at first, what we need to do, we need to find the capacitance whenever we're looking at the series combination, capacitance for series combination. Remember we said that whenever we have capacitors in series, right, the total capacitance is given as this formula to say 1 upon CT is equal to 1 upon C1 plus 1 upon C2, right? Now, there's another way we could write this. Whenever we just have only 2 capacitors in series, or in parallel, in series I should say, we could say that CT is equal to C1 times C2 divided by C1 plus C2. And if we were to go ahead and calculate that, we have the 2 microfarads multiplying by the 4 microfarads, divide that by 6 microfarads. When we do the numerator, we get 8 times 10 to the negative 12 farad square divided by the 6 microfarad, which is the same thing as 10 times 10 to the minus 6. So by way of doing all of that, we realize that CT, right, or we can say C1 and 2 is equal to 1.3 times 10 to the minus 6 farads. So that's for when we have capacitors in series. Now, let's just redraw the circuit quickly. So here we have the circuit again now. So we just worked out a while ago what happens when we have those capacitors in series. Now, those two capacitors right here is just is just one. We can classify that as one single capacitor now. So this capacitor is the 1.3 times 10 to the minus 6 capacitor, farad, right? And that is now in parallel with a 6 microfarad capacitor, if you follow me. 6 microfarad capacitor. So to find the total capacitance in series, we are going to add them. So CT is going to equal to C12 plus C3. C12 was determined to be 1.3 times 10 to the minus 6 plus the 6 microfarad, which is the same thing as saying times 10 to the minus 6. So by way of adding up all of this, now we get that CT is equal to 7.3 times 10 to the minus 6, right? 6 farad. Good. So that's our total capacitance. So this answers this question. So this is 7.3 times 10 to the minus 6 farad. Now the question says to us to find the net charge. The net charge is the total charge that is supplied to the system. Now, to find the net charge, we must know the net capacitance and we must know the net voltage or the total voltage. So using this equation that says C is equal to Q, right, divided by V, we can transpose. So by transpose, we can see that Q is equal to C times V. Good. So by way of just doing the mathematics, right? In this event, we're finding QT, right? And QT has to come from when the capacitor is totally charged, or the total capacitance, right? We can use the total capacitance times the voltage to find the total charge. So with that being said, our total capacitance was 7.3 times 10 to the minus 6 times the voltage, which is 12 volts. So QT is nothing more than this particular value. When you multiply 12 by 7.3 times 10 to the minus 6, we get a value to say 8.76 times 10 to the minus 5 coulombs, or we can say that is going to be 88 microcoulombs. That is our total charge. Now it moves on to say to us that we need to calculate the charge on Q1 and the charge on Q2. All right. But before, you see, the thing is, whenever you have capacitors in series, right, the charge on Q1 is going to be the same charge on Q2. Because in a series circuit, current remains the same. So, if I know the charge that is flowing through Q3, right, then because let's look at it this way. Imagine that the current is flowing like this. Let me see if I can use a different color. Imagine that the current is flowing into this node. That is my total current. Then we're saying that some of the current is going to flow down here like this, and some of the current is going to flow that way. By obviously Kirchhoff's first law, some of the current entering the junction is equal to some of the current leaving the junction. So in essence, it's the same thing when it comes on to charge. Kirchhoff's first law speaks to the conservation of charge, which tells us that whatsoever amount of charge you start out with, then that's the same amount of charge that you should end up with. So in essence, we're saying here that my QT, right, is equal to Q, let's call it Q1, right, plus Q3. Follow me? Now, because I know QT, right, I can find Q3 by way of using this formula to say that Q3 is equal to C times V. So C3 times V. Now, based on this circuit, we have a parallel combination here. So the voltage across C3 is going to be the same voltage across C1 and C2 because it's a well, not 100%, but just imagine that because it's a parallel circuit, right? Then the total voltage or the voltage across C3 is going to be 12 volts. So C3, which is 6 times 10 to the minus 6, right, times 12. When I do work out that, I get that C3, or Q3 rather, Q3 I should say, is 72 times 10 to the minus 6 coulombs. Following? And from the fact that I know that QT was determined to be 88 microcoulombs, right? And if I just calculated what Q3 was, Q3 is 72 times 10 to the minus 6, then I can find what Q1 is, right? And this is obviously coulomb. So by just manipulating the equation to say 88 times 10 to the minus 6 minus 72 times 10 to the minus 6 as well gives us Q1, right? Then we can see that the charge, right, the charge stored, the charge on Q1 is going to be 88 minus 72. So Q1 is actually equal to 16 times 10 to the minus 6 coulombs. So we're saying Q1 is equal to this. So Q1 is actually coming at this point. You understand? And this is where Q3 would have been, and then now QT would have been at that point. So because of this nature now of this whole series combination, then what we're literally saying is that the charge flowing through C1 and C2 is going to be the same. So Q2 is going to still be the same, 16 times 10 to the minus 6 coulombs. Right? I would beg to agree that that's the case. But if anything, I'll clarify that eventually if that's not the case. But I think that should be the case. All right, moving along now. Now, guys, whenever a capacitor is being charged, we said it already that work has to be done, right, to charge a capacitor. Now, just imagine that this is a capacitor, right? Parallel plate capacitor. This is one plate. This is another plate, right? And this is connected to some power source. So this is connected to some power source. Now guys, let's look at this. If I'm sending the electrons in the circuit in this direction, right? If current is flowing like this, right? What you would observe is that electrons are going to accumulate on this plate. Good? Now, remember that positive attracts negative. So what you would realize is that for this particular plate, right, electrons will be moving towards the positive. So if electrons are moving out of this material, then what we have left is positive charge inside of it, right? Now, two things are taking place, right? One plate is electrons are being added to that plate, while another plate electrons are being removed. In the entire process, right, work is being done to add the electrons to one plate and to remove the electrons from the other plate. So if you look right here, it says that equally work is done to remove electrons from the positive plate as negative charge are attracted to the positive region. So this is the positive region of the battery, and this is the negative region of the battery. So you know, battery has two terminals, positive and negative. So just imagine, guys, if we are doing work to deposit the negative charge electron on the negative plate, right? So we're saying that we're putting negative on this plate. So this plate now becomes negatively charged, right? And we're taking electrons from one plate, right? So this plate becomes positively charged. Work is being done. There's no question about that. Now, in order for us to find the work that is being done to charge a capacitor, right, we can plot a simple graph, right? So let's imagine that this is what is happening whenever we're charging a capacitor. So at first, the capacitor would not have any charge on it. So it would be at zero. Now, by increasing the voltage, right, I am increasing the charge that is being stored, because the more work that I do, right, is the more charge that is being able to store. So more charges are stored on the capacitor, so we get this directly proportional relationship. And if you can recall, the equation that says Q, right, is equal to CV, we have a directly proportional relationship here, right, to say that as the voltage increases, the charge increases. Now, to find the work that is done to charge the capacitor, right, we have to take into consideration the area underneath the graph. If you can recall something spectacular, when we're dealing with potential difference, work is equal to, let me see if I can remember from this equation. V is equal to the work done divided by Q. So obviously work is going to equal to V times Q, right? Now, this is not the actual work in this part. The work for the capacitor here is going to be the area underneath the graph. And underneath this graph, we have a triangle. And we know a triangle, whenever we're trying to find the area, we use the formula to say half the base times the height. So what is my height? My height is my voltage. My base is my Q. So it tells us that the work that is done to charge a capacitor is equal to half, right? Half the base, which is Q, right, times the height, which is V. So this equation here, half Q times V, tells us the work that is required to charge the capacitor. So you have to use the area underneath the graph to find it. to find the work that is done. Good. But there are other equations that can come arise. If we recall that Q is equal to C times V, we can substitute Q in this equation. If I substitute Q in this equation, I am now left with this equation to say that the work done is equal to half V squared times C, right? And also, if I were to substitute V in this work equation, right, I would have now seen that the work is now equal to Q2 divided by 2C. So that is something that you should pay attention to, right? The several equations that you can use. So you can use this equation to find the work, right? And you can also use this equation to find the work. But the root equation is this one that I showed you a while ago. That says work is equal to a half Q times V, which is coming from the area underneath the graph right here. All right. Now, this is just some information to explain to you what is happening whenever we're charging a capacitor, right? It says electrons move from negative to positive around a circuit. That is by nature of how electrons actually flow. Now it says that the electrons are deposited on plate A, making it negatively charged. Now electron travels from plate B to the positive terminal of the battery, giving the plate A a positive charge, right? It says now electron built up on plate A, and it says an equal amount of electrons are removed from plate B, creating a potential difference across the plates. Follow me? It says now when the potential difference across the plates equal the potential difference across the source, we say that the capacitor is fully charged. So if you start out with 12 volts as your power supply, right? And when you charge your capacitor, and you now realize that the voltage is now 12 volts across it, or the potential difference is now 12 volts, or 12 volts, then that is when the capacitor is fully charged. So if you get a scenario that says the capacitor is fully charged, it means that whatsoever voltage that the power supply has, right, are provided to it, that's the same amount of potential difference that is going to be measured across the capacitor. Now, mind you that this is a circuit that shows you when the capacitor is being charged. When a capacitor is being charged, right, it is connected in series with the power source. Follow me? Good. Now, we're going to talk about discharging a capacitor eventually, but at this point, let's just talk about charging a capacitor for now. All right, so I realized I did not structure the thing a little bit more in a fluid way, because this could have been this slide could have been further up to talk about this, but either way, it's already here, and we're going to just talk about it. Now, there's something about capacitors, right? There are times when a capacitor can be made with two different dielectrics. Now, whenever we see a capacitor looking like this, where we have one dielectric here, right, and one dielectric here, touching together like that, right, we say that we have capacitors that are in parallel. So this arrangement is showing us when we have capacitors in parallel. And if we can recall how we find the capacitance for capacitors in parallel, we sum up the capacitance. So CT is going to equal to C1 plus C2. Now, to find C1, we have to then look at our equation that we looked at to say that capacitance is equal to epsilon times the area divided by the charge, divided by the distance rather. Now, in each of these capacitors, because they are different K values, epsilon is going to be a different value. So this is going to be the epsilon 1 and this is going to be epsilon 2, right? But because we can recall that K is equal to epsilon, right, divided by epsilon naught, then we can transpose that equation to find what epsilon is. So epsilon 1 is going to equal to K1 times Q times epsilon naught. And just substituting that, we get that C1 is equal to K1 epsilon naught times the area of that plate, right? Because imagine that this is the entire area A, right? But if you divide it in a half, then this capacitor now has an area of A divided by 2. So that's why you see we have A divided by 2 here. And similarly for this capacitor, C2, right, you would do the same procedure right here to find that capacitance. Now, there's also another type of arrangement. When you see we have capacitors where the dielectric are stacked on top of each other like this, right? We say that this capacitor is going to be capacitors in series. And if you can remember, whenever we have capacitors in series, right, we say that the total capacitance is equal to 1 upon C2, well, my bad. So 1 upon CT is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3, and it continues, right? So what you would just have to do is to find what C1 is even individually, right? And C1 here would be K1 times epsilon naught times A. The area doesn't change. The area of the plate will remain constant in this case. So that doesn't change. All right. Now, divided by the distance. Now, imagine that each dielectric, right, has the same thickness. If each dielectric have the same thickness and you have 3 different dielectrics, then it means that your distance now is now going to be D divided by 3. So our D divided by 3 would tell us, all of this right here would tell us the capacitance on C1. So you would have to work that out individually. Then you do it for C2, then do it for C3. Then you sum up all of this thing and find the total capacitance. Nothing hard. I mean, now if you look at this scenario here, right, we have different dielectrics. We have one dielectric K1 here, right, and then we have another set of dielectric that are stacked on top of each other. Remember, we said that when capacitors are stacked on top of each other, then we are having a type of series connection. So remember, in series, to find that total capacitance, you have to say 1 upon CT is equal to 1 upon C1 plus 1 upon C2. Or we could make it short to say that CT is equal to C1 times C2 divided by C1 plus C2. Good? So with that being said, we could have found the capacitance of those two capacitors in series. Then we would then left with this thing here. So let's see if I can redraw the plate, right? So by way of redrawing this, we now have two dielectric, right? Or two capacitors rather. So this CT would have told you the capacitance of this capacitor, right? Then now this K1 here is giving rise to another capacitor that is now in parallel with this one. So in total, you have two capacitors that are in parallel with each other. We know that to find the capacitance for capacitors that are in parallel, then you would have to add them up. So the total capacitance really is going to be C1 plus C2, similar to what you would have had right here. You understand? So that's how you would have to consider that. But you just also have to remember that in this regard right here, the distance of separation is D divided by 2. All right? So that's just something to take note of. Here we have a question, but I'll leave this question for you to solve. Now, we will end this lesson on this question, right? Then, to pick up the lesson next time, we'll talk about discharging capacitors.